Good morning. This class is on fluid mechanics. Topic is Newton's law of viscosity. Newton's law of viscosity, that is the topic of today's discussion. In the last class, few words were spoken about viscosity. There you have seen that one term is there that is called shear stress, and another term which is called velocity gradient. First, let us discuss about shear stress. You take any object. Okay, you take any object and on the surface of the object you take a point. You take one point and surround that point by a small area. Surround that point by a small area. The area may be arbitrary. It need not to be rectangular or square or circular. It may be arbitrary. Okay? And consider a force which is acting at that point at any angle. Orientation of that force vector may be anything. Okay? Now resolve that force into three components. Components along x, y and z axis. We are using here rectangular Cartesian coordinate system, and it is your choice where you will take the x-axis, where you will take the y-axis, where you will take the z-axis. That is your choice. Okay, but here we are using rectangular Cartesian coordinate system. First you choose the x-axis and accordingly you take the y and z-axis. Now resolve the force into three components, x, y and z. Where one thing you do here, that you take that x-axis along the tangent of the surface at that point, the point through which the force is acting. You draw a tangent on that surface, that small surface. Okay? So again, along the tangential direction you take the x-axis, perpendicular to that, but again that is tangential to that surface at that point, take the y-axis, and z is the normal axis, normal at that point on that surface, that is the z-axis. So you this way, you have chosen this way the coordinate axis. Now resolve the force into these three components, fx, fy and fz. Component of force along x, y and z axis, and suppose that small area is delta A, small delta A, capital A area. Okay. Now Fx divided by that delta A is equal to force per unit area, but this force is tangential. Mind it, this force is tangential. Fx divided by delta A. So this is what? Force per unit area. This is stress for that area. Similarly, Fy by the same area delta A is equal to stress at that point in the direction of y for that small area, and accordingly Fz by delta A is also a stress which is normal stress because direction of Fz is normal to the surface. Now, if you make that small area delta A vanishingly small, in calculus you write that delta A tends to 0, like that, vanishingly small. Then, if the limit exists, that fx by delta A, if that limit exists, then fx by delta A, that becomes, or since we are using calculus here, so instead of writing fx, fy, fz, it's better to write dfx, dfy, dfz, and the resultant force is df. Okay, df is the resultant force. Means df is the force which has three components: dfx, dfy, dfz. So the ratios are dfx delta A, means dfx by delta A, dfx by delta Y, and dfx by delta dfx by delta A, dfx by dfy by delta A, and dfz by delta A, like that. Okay, and if the limits exist, then those becomes df dA, means df by dA, dfx by dA, then dfy by dA, then dfz by dA, like that. So these are what? These are stresses at that point when you make delta A vanishingly small. When delta A approaches 0 and if the limit exists, those becomes df dA, dfx dA, dfy dA, and dfz dA. So these are called stresses. Two of them are tangential stresses. Those tangential stresses are called shear stresses. dfx dA and dfy dA, those are tangential stresses. Those tangential stresses are also called shear stresses. And that dfz dA, that is called normal stress. So this is for three-dimensional case, and in actual practice, all the cases are three-dimensional. But in your fluid flow problems, if in any one of the directions the changes in the flow variables are negligibly small, in that case you can say that the flow is taking place in two dimensions only. So say for our case, in the direction of z, there is no change. So you don't consider z for this case, for the analysis of that, for the discussion of Newton's law of viscosity. So here, for our sake of simplicity, you take x to be the horizontal axis and y to be the vertical axis. Along x, the component of velocity is u, small u. Okay, and along y, there is no change in velocity. We are assuming this way though. We are assuming the flow field to be this way, that u depends upon only x. When x changes, u changes, and for any other changes, means in the direction of y or in the direction of z, there is no change of u. U depends only upon x coordinate. Okay. Now consider laminar flow. You know laminar flow. Take two layers of fluids. Layers can be considered here as solid plates. The molecules of one layer do not mix with the molecules of the next layer. If we assume like that, when the flow velocity is sufficiently low, in those cases, you can consider the flow field to be laminar, where there is where the one layer of fluid moves with respect to the another layer, like a solid surface. So frictional forces will be acting in between the layers. Okay. So in the direction of y, you take one layer of fluid, and at delta y distance apart, you take another layer of fluid. Means from x-axis, the distance of that layer will be y plus delta y. For the first layer, which is at a distance of y, you consider the flow velocity to be u, and at a distance y plus delta y, you consider the flow velocity to be u plus delta y. U plus delta u, not y, u plus delta u. So for a distance of delta y, there is a change in velocity of delta u, like that. Then what is the velocity gradient here? It is u plus delta u minus u, that is the change in velocity between the two layers. U plus delta u minus u, that is the change in velocity in for the two adjacent layers, and the distance between them will be what? It will be y plus delta y minus y, that is delta y. So result is what? Delta u by delta y. Delta u is the change in velocity, delta y is the change in distance. Right? And now you make delta y to tend to 0. Means when delta y approaches 0, if the limit exists, so this delta u by delta y becomes du dy, means du by dy. So this is the velocity gradient. And suppose the shear stress, two layers are there, and tangential stress is the shear stress. Suppose shear stress is here denoted by tau, Greek letter tau. Then, according to Newton's law of viscosity, this shear stress tau is directly proportional to that velocity gradient du dy. So you will write this way: tau, this is proportional to du dy. That means tau is equal to a constant multiplied by that du dy. That constant is represented by the Greek letter mu. Greek letter mu. Okay? And that constant of proportionality is called viscosity, or coefficient of viscosity, or coefficient of dynamic viscosity. Only viscosity, or coefficient of viscosity, or coefficient of dynamic viscosity. Right? That constant of proportionality is called viscosity. This viscosity is not a constant, it depends upon pressure, it depends upon temperature. For liquids, this viscosity, this dynamic viscosity, coefficient of dynamic viscosity, this viscosity for liquids depends largely upon temperature, but it is almost independent of pressure. Due to change in pressure of liquids, there is almost no change in viscosity. But for gases, for a little change in either in temperature or in pressure, there is a noticeable change in viscosity. So for gases, you have to consider the change of viscosity for the changes in for the changes in pressure as well as in temperature. But for liquids, only you consider the changes in temperature. For change in pressure, there is almost no change in viscosity. One more thing, I have mentioned that this viscosity is a constant, but not for all the fluids. Few fluids are there, such as water, air, etc. Few fluids are there for which this viscosity is a constant, means where shear stress is directly proportional to velocity gradient. This is obeyed, this law is obeyed only by few fluids, such as water and air. The fluids which obey this law are called Newtonian fluids, because this law, shear stress is proportional to velocity gradient. This law is called Newton's law of viscosity. So the fluids which obey this law are called Newtonian fluids, and any other fluids which do not obey this law are called in general non-Newtonian fluids. Among non-Newtonian fluids, there are more categories like Bingham plastic fluid, dilatant fluid, pseudoplastic fluid, thixotropic fluid, rheopectic fluid, like that. Okay. And in our first year course of BTech, all the fluids will be considered as Newtonian fluids, if not mentioned. And if in your given numerical problem, if something is mentioned about the relation between that shear stress and velocity gradient, and those things will be mentioned only for non-Newtonian fluids. Okay. But in general, in our mechanical engineering courses, most of the fluids are taken to be Newtonian in nature. Okay. So one thing you have to notice here, that the direction of the velocity u and the direction of y are perpendicular to each other. They are not in the same direction. Direction of u is along x axis and direction of y, that is perpendicular to x axis. Okay. The velocity gradient, where we write du by dy, the direction of u and direction of y are not same. And direction of u and direction of y are perpendicular to each other. This law is so simple to use. Don't get confused. Okay? Many students commit the same mistake. They take the direction of u and direction of y to be the same. That is wrong. Okay? So this was all about Newton's law of viscosity. Okay? In the next class, I will discuss something about non-Newtonian fluids. Okay? Thank you. Have a nice day.